All right, I guess we're good now. Guess somebody had to hit start stages or something, and it was like
Yes,
default.
I needed to do that. That was my bad.
Okay, cool. All right. Trying to my screen orientation to flip. Okay, I guess we are ready. Um, okay, so today we're finally going to see how the SumCheck protocol works. Last week I was planning on covering that, but kind of just wound up covering an application. So I stated like what the protocol did and what its costs were, and then tried to sketch Spartan, which is a snark for R1CS that uses the SumCheck protocol. I don't know how well that went. There's always this problem where, in order to appreciate why the protocol is useful, you have to see an application. Um, but it might be hard to see, to understand the application if you don't know how the protocol works. So there's kind of a chicken and egg problem. You have to start somewhere. So hopefully there was some value to seeing the application last week, and we're going to see a bunch more applications. The SumCheck protocol is sort of a hammer that's incredibly powerful, but it just takes a little bit of practice to get used to, how it's applied. It's sort of once you understand how to use the hammer, it's very natural, but until you've used it several times, it doesn't feel natural. Okay, so the problem that the SumCheck protocol solves is the following. So we're going to let little g be an n-variate polynomial over some field. And let's say for concreteness, that the degree of g in each of its n variables is like 2 or 3 or something. Let's say 3 for now. In some applications, in many applications it's 3, but sometimes it's just as little as 2. And the goal is to compute the sum of g's evaluations over all inputs in 0, 1 to the n. Right. So like the domain of g, because it's a polynomial over field, is field to the n, but the verifier kind of only cares about inputs in 0, 1 to the n. So the domain of g is much bigger than what the sum is over, but the verifier wants to sum up g's evaluations only over the Boolean inputs. Okay. And in many Snark applications, you should think of n as something like log of circuit size. If the prover is proving that it knows a satisfying assignment to some circuit, you should think of n as maybe log of circuit size. And so, computing the sum explicitly, there are something like circuit size many terms of the sum. Okay, and we don't, succinctness means we really want our verifier to run in time, like logarithmic in the circuit size instead of linear in the circuit size, which is one reason the verifier doesn't want to compute the sum on its own. Okay, and the SumCheck protocol is a very powerful way to offload the hard work of computing the sum to the prover. So as far as verifier costs go in the SumCheck protocol, there are n rounds of the protocol, 1 per variable of g. So think of that as like logarithmic in the size of the circuit if you're trying to design a snark for circuit set. And ultimately, it's a public coin protocol, so we can apply fiat Shamir to get rid of all the rounds. in each round, the prover sends a degree 3 univariate polynomial. Right, so that's only like 4 field elements or something sent in each round. So the total communication cost is just, proportional to, again, in applications like the logarithm of the size of the circuit we're, proving a statement about. So in practice, that's often just like several dozen field elements, up to up to several hundred field elements, depending on how big the circuit is. Several hundred field elements is, you're talking on the order of a handful of kilobytes or something like that. So in practice, let's just say proof size is, let's say, 1 to 10 kilobytes off the top of my head. If you run the SumCheck protocol just once, I'd have to think a little more carefully to know if it's closer to 1 kilobyte or 10, but that's the right range roughly. And the verifier, kind of checking each message, does a sort of a consistency check in each round, which it runs in time like linear in the size of the message in each round. So in total, the verifier does order n field operations, and evaluates G at a single point R. Okay, and so from the verifier's perspective, this protocol is kind of a reduction from the hard task of evaluating G at these 2 to the n terms and summing up the results, to the hopefully easier task of just evaluating G at a single point R. So hopefully G of R is easier, for the verifier to compute, than the desired answer, which is, again, the sum over all 2 to the n Boolean inputs of G of X. Okay, so as long as that's the case, then, this protocol was useful for the verifier. It sort of let the verifier offload this very hard task to the prover, and the verifier is left with the easier task of evaluating G at just a single point R. Okay, that is the cost of the SumCheck protocol. So now I'm finally ready to tell you how it works. But let me just pause here and see if there are any questions at this point. Questions?
None so far.
Okay. Great. All right. So the protocol starts with the prover sending the claimed answer. Let me call that claim C. Okay, and we'll call that like round 0. And you could also think of this as this claim can be implicit you can sort of derive this claim from the first round message. But anyway, let's say that the prover starts by explicitly sending the claimed answer, and then we move on to round 1. Okay, so on round 1, the prover sends a univariate polynomial and let me call the actual thing that the prover sends Si of X, which is claimed to equal the following univariate polynomial. S1 of X, H1 of X. Okay, so S1 of X is what the prover actually sends. H1 of X is what the prover should send if the prover is honest. Okay, so H1 of X is the following. So we're going to sum over everything but the first variable. Okay, so now we're going to sum over like x2 up to xn in 0, 1 to the n minus 1 of G of X, capital X here, comma x2 up to xn. Right, so we're summing now, we're sort of leaving the first variable out of the sum and leaving that variable like as a variable. Okay, And, something a little crazy is happening here, right? Because, there are a huge number of terms in the sum. There's 2 to the n over 2 terms in the sum. But each term is a degree 3 polynomial in the single variable x. Right? Because G itself, I said, has degree 3 and at most 3 in each variable. Okay. So there's a huge number of terms, but each term individually is very simple, right? Each term individually, a degree 3 polynomial is like, C0 plus C1 times x plus C2 times x squared plus C3 times x cubed, right? Like very simple, 4 coefficients or whatever. So each term is very simple. There's a huge number of terms, but once you sum them all up, what comes out is still just a degree 3 univariate polynomial. And so, S1 and H1 are very simple objects. They just have 4 coefficients, even though H1 was defined by this giant sum. Okay. Again, it turns out in the sum check protocol, at least from the prover's, perspective, it's most natural to deal with these polynomials, specify them via giving 4 evaluations of them rather than 4 coefficients in the standard monomial basis. But let's not worry about that much yet. So the prover in round 1 sends a degree 3 univariate polynomial, so just 4 coefficients or something, claimed to equal this degree 3 univariate polynomial. Okay, and so if the prover is honest, right, then so if the claimed answer is like equal to the real answer and S1 of x equals H1 of x, then the claimed answer will equal S1 of 0 plus S1 of 1, right? So what's going on here is if H1 sort of takes the original sum that the verifier is interested in, and it cuts out the first variable from that sum. Okay, but if you set that first variable to 0, you get out the first half of the terms in the sum where x1 was 0. And if you set that first variable to 1, you get out the second half of the terms in the sum, meaning the terms where x1 was 1. And if you add those two together, you get the whole sum. Right. So we defined the honest prover's message specifically so that this check would pass. So again, this is like the sum of the first half of the terms, and this is like the sum of the second half of the terms in the whole expression that the verifier cares about. Okay, so this is called like the round 1 consistency check. And again, we explicitly defined the honest prover's message so this check would pass. Okay, and yeah, and the point is, like, if S1 were honestly specified, were equal to H1, and this equality held, then the claimed answer would indeed be the right answer. So what the verifier is left to check now that this consistency check passed, is to try to ascertain, does S1 equal H1? Does S as polynomials? Are these two polynomials the same polynomial? Okay, and we should be getting pretty used to the following technique at this point, which is if you want to know whether two polynomials are the same polynomial, it's enough for the verifier to pick a random point and confirm that they're equal at that point, right? Because as long as the polynomials have reasonably low degree, if they're not the same polynomial, they can't agree at many points, right? So if they happen to agree at the random point picked by the verifier, then it's very, the verifier has a lot of confidence they are in fact the same polynomial. So to do this check, the verifier picks R1 at random from the field, sends R1 to the prover, and wants to check that S1 of R1 equals H1 of R1. Okay. Now, here's the thing. S1 was explicitly sent by the prover to the verifier. So the verifier can compute S1 of R1 on its own. Right, because the prover sent S1 to the verifier. It's a degree 3 polynomial. It takes like a handful of field operations to evaluate a degree 3 polynomial at a field element R1. Okay. The problem is the verifier, has no idea what H1 is, right? H1 is defined via this expression, which is almost as complicated as the original problem, right? It only cut one variable out. So the verifier, cannot compute H1 of R1 on its own. All right, but that's what the future rounds are for, right? Like, note H1 of R1 is, this is just the definition of H1 up here. So it's sum over, x2 up to xn in 0, 1 to the n minus 1 of g of R1 comma x2 up to xn, right? So this expression here, this is exactly the kind of expression that the SumCheck protocol is designed to compute. Now the polynomial is in n minus 1 variables instead of n variables, right? So we just apply SumCheck sort of recursively. You can think of SumCheck as either a recursive, protocol or an iterative one. If you want to think of it recursively, we just recursively apply SumCheck to the n minus 1 variate polynomial. Maybe I'll give it the name G prime of, x2 up to xn, defined to be G with the first variable fixed to R1. Okay. So, writing out what that means is, we move to round 2. So on round 2, the prover sends, a degree 3 univariate polynomial S2 claimed to equal sum over x3 up to xn in 0, 1 to the n minus 2 of g of R1 comma x comma x3 up to xn. Yeah, and the verifier does its consistency check. That S1 of R1 indeed equals S2 of 0 plus S2 of 1. Again, we defined. Let's give this thing a name. If the prover's honest, what its round 2 message would be. Let's call it H2. We define H2 so that this consistency check will pass if the prover's honest, right? If P is honest, and indeed S2 equals H2, this check will pass. And so on and so forth. So that's how SumCheck proceeds. So every round, the verifier picks, another random field element and sends it to the prover. And then, they use the next round to confirm that, S3 of R3, S2 of R2 equals H2 of R2, again, so in round 3, H2 would kind of implicitly get broken down into, some, there'd be a consistency check in round 3 where, H2 of R2 gets replaced with S3 of 0 plus S3 of 1, where this is the prover's round 3 message, and so on and so forth. Okay, and so, this proceeds round by round until in the final round, the verifier picks an RN from the field at random and needs to check that SN of RN equals what would be HN of RN, but HN HN, if you work it out, is just G of R1 up to RN, right? Like it's, every round, there's one fewer variable to sum over. So by round n, there's no sum anymore, right? By round n, every single one of the n variables has been fixed to a random field element, and now there's no sum, and hn of rn, what the prover sends in the final round, if the prover's honest, is just in the final round the prover would send, so let Sn of x, which is just g of r1 up to rn minus 1 comma x. And then once the verifier sort of picks a random value in the nth round, the provers, the thing that's left to check is just a single evaluation of g. Okay. So that's it. So just writing it out in full. So just writing it from scratch. So round 0, the prover sends the claimed answer C. Round 1, the prover sends a degree 3 polynomial S1, which again is claimed to equal this H1, which is summing over all but the first variable. So degree 3 univariate polynomial. The verifier checks that the claimed answer is S1 of 0 plus S1 of 1. The verifier picks R1 at random from the field, sends it to the prover. Round 2, the prover sends S2 of X. Again, it's degree 3. The verifier does its consistency check. S1 of R1 equals S2 of 0 plus S2 of 1. The verifier picks, an R2 at random from the field, sends it to the prover. And in general, in round I, the prover sends SI of X. The verifier checks SI minus 1 of RI minus 1 equals SI of 0 plus SI of 1. The verifier picks RI at random, sends it to the prover, and that's the end of the round. And then finally in round N, at the very, I guess I'll write it all out. The prover sends, Sn of X, verifier checks, as usual, Sn minus 1 of Rn minus 1 equals Sn of 0 plus Sn of 1. Verifier picks Rn at random from the field, and finally confirms Sn of Rn equals G of R1 up to Rn. And again, this is why the verifier, needs to evaluate G at one point, namely, R1 up to Rn. That's the sum check protocol. Okay. And sort of I presented it in a way that should make soundness and completeness kind of clear, right? So completeness requires that, if the prover is honest throughout the protocol, all the verifier's checks will pass. And we sort of explicitly define each polynomial SI to make this check pass. So all the checks wind up passing. And then soundness works as follows, right? Like if the prover begins by sending the wrong answer, then in order for this the round 1 consistency check to pass, S1 better not equal H1, H1 being the polynomial the honest prover would send. Okay, and then, if S1 does not equal H1, with overwhelming probability over the choice of R1, S1 of R1 will not equal H1 of R1, right? Because they're both degree 3 polynomials. And so if they're not the same polynomial, they can agree on almost 3 points, but R1 is chosen from the whole field. And so, if R1 does not equal one of the 3 points that S1 and H1 agree at, then the prover is left with the false claim in round 2, which means in order for the verifier's consistency check to pass in round 2, S2 better not equal H2. And again, you say the same thing. Well, if S2 doesn't equal H2, then, with probability, 1 minus 3 over field size, S2 of R2 will not equal H2 of R2. And in that event, the prover is left with the false claim at the start of round 3, and so on and so forth. So basically, if the prover starts with the false claim at the beginning of the protocol, in order for it to pass the verifier's check at the end of the protocol, there must be at least one round where the prover gets lucky, right? And so you just apply a union bound over all rounds, so the soundness error is at most the number of rounds, which is n, times the probability the prover gets lucky in each round, which is like 3 over field size in this case. So as long as your field size is much bigger than 3n, the soundness error is small. So that's the sum check protocol. Okay, let me pause here, see if there are any questions.
One question that was shared in chat was basically like, where does the multilinear piece come into this? And is the reason that this whole thing works because we can go from multilinear extension to, or from multivariate to multilinear using EQ and degree check?
Yeah, so multilinear stuff comes in. So, okay, it's very clear that you want, many variables, right? So univariate just doesn't make sense really with sum check, more or less, right? What's going on is, there is a trade-off, I think, as I mentioned last week, where you can reduce the number of variables in an application, but as you reduce the number of variables, you increase the degree of the resulting polynomial in each variable, right? And so, the proof size of sum check is number of variables of the polynomial times degree in each variable. Okay, but what's going on is roughly, if in applications, if your circuit, well, let's see, how do I want to say this? If your circuit has size, I don't know, like C, then if you use, k-variate polynomials, so we need polynomials, capturing the circuit to apply sum check to in order to use the sum check protocol to prove something about the circuit. So if those polynomials, that you sort of, as a protocol designer, you have the flexibility to choose what polynomials to use and then to apply sum check to. But generally, if you use k-variate polynomials, the degree in each variable is going to have to be at least n to the 1 over k. And so the sum check, proof size in general is k times n to the 1 over k. And you don't, so with multilinear, if you use multilinear polynomials, k will be about, sorry, I guess by n I meant circuit size. Sorry about that. So multilinear polynomials, k will be about log circuit size. And then the degree in each variable becomes 1, 1 or 2 or something. Right. And what's going on is we're just, if k times something to the 1 over k is minimized by setting, k to be log n, log bits 2 of n. That's when then this becomes like log n. Then k times n to the 1 over k is about log n or so. So if you wanted to use, if k was 1, then the proof size is n. And this is just not succinct at all. This is the proof is writing down the value of every gate in the circuit or something. Right. And so this is why many variables are powerful. If you use many variables, you can have you can deal with polynomials that have very low degree in each variable, and that's what gives you short proofs, fast verifier, whenever you use the SumCheck protocol. And so as we see more applications, everything will become clearer. But yeah. So maybe I should so last week was Spartan, which again I will cover it, from scratch, again, because now that we know the SumCheck protocol, it's worth seeing it, again. But yeah,
I'm going to propose that we first check in and make sure that the original question Scott wanted to ask was getting answered, and then I want to go back to questions on what you've talked about so far instead of covering more, if that's okay.
Okay, sounds good.
It's actually a really interesting answer, and the question that I was asking, it was rooted in a little bit different thing, like this multivariate and uh, multilinear distinction. I just wanted to ask to help a bit to track things for a student like me, when we should be aware and what should be, where should we direct our attention when we switch between multilinear, or when do we need multilinear, and what dangers, I don't know, does it bring with it. I clearly remember that thing that you mentioned, that you distinct about single mention for multilinear, and it is distinctive property of multilinear, but it's quite a bit confusing to work with and to follow.
Yeah, it's a good question, and it's a little bit tough to answer. So I'd say in general, the verifier costs are, if you use k-variate polynomials, are like k times n to the 1 over k, where n is like circuit size, or just like the number of terms in the sum you're applying SumCheck to, right? And this is minimized when k is log n. So if your sole goal is to this is really like proof size or whatever, is to minimize proof size, you should use multilinear. Like, you should just always use multilinear if your goal is to minimize proof size. Furthermore, when you use multilinear polynomials, they're really nice for the prover. So if we haven't discussed how the prover computes, for the prover computing, the message it's supposed to compute in each round.
Is it basically because of he can cache the values while he go through the rounds?
Yeah, I would say that's right. That's how the fastest SumCheck prover implementations work. But really, everything stems the reason multilinear polynomials are so nice is boils down to multilinear Lagrange interpolation. And this is a topic I always debate whether to cover it or not. I mean, I think how you make the SumCheck prover super fast is the key to performative snarks, but it's also a very detailed, technical, topic.
I think a primary question here is we spent a bunch of time talking about multilinear things, talking about the Schwarzschild lemma and that kind of thing.
Mm.
Now we're talking about multivariate polynomials, and we're talking about the sum of g of x over a hypercube. Do we use multilinear anything in SumCheck protocol or not? It seems like you didn't actually use it in your presentation today.
Yes,
Yeah.
and a little bit to this question is if there are kind of general food guns that we can encounter when moving multilinear to multivariate.
Great. So yeah, so this is why this question is the benefit of covering an application first. So why we spent last week seeing an application instead of how the protocol works. And so I think to answer the question, I do have to refer briefly to last week. So since that's the only application we've seen. So, we wanted to check last week that, if little a, little b, little c were vectors in field to the capital N, we wanted to check that AI times BI equal, minus CI equals 0 for I equals 1 to N. Yeah, and so how did we do that, right? We applied SumCheck. Well, let's see. So the verifier picked an R in field to the log N at random. And it confirmed with SumCheck that the sum over all x in 0, 1 to the log N of EQ twiddle of R comma x times a twiddle of x times b twiddle of x minus c twiddle of x was 0. And so, it applied SumCheck to the polynomial g of x equal to what's inside this sum. EQ twiddle of R comma x, I'll just write it out again just to be completely clear, a twiddle times a twiddle of x times b twiddle of x minus c twiddle of x. Okay, so what you see here is G is not multilinear, right? G has degree 3 in each variable. But G is built out of multilinear things.
Uh-huh.
So EQ twiddle's multilinear, A twiddle's multilinear, B twiddle's multilinear, C twiddle's multilinear. That's how it always works. I think I mentioned last week, if G itself were multilinear, there's actually, in the sense, no reason to use the SumCheck protocol because then the sum.
Sorry.
Yeah,
Isn't the degree 2 instead of 3?
It's 3. So this gives you degree 2, A twiddle of x times B twiddle of x.
And equality.
Then the EQ, and then the multiplication by EQ of R comma x makes it degree 3.
Oh, yes, it's important. Thank you.
Now we now have ways to sort of act for prover costs. It winds up that the SumCheck protocol applied to this G. So the EQ thing doesn't turn out to contribute to the prover's costs in the end. But you need to be very clever to make that the case. There's some very recent ePrint that does that. Anyway, and so yeah, I mean the fact that so I'd say the fact that we're using multilinear extensions, EQ twiddle, A twiddle, B twiddle, C twiddle, is helping both the prover and the verifier, right? It's actually what makes the proof size the lowest, makes it 4 log n or something, 4 field elements sent in each of the log n rounds. I think if you use non-multilinear things, the number of rounds would go down, but the proof size in each round would go up in a way that more than compensates for the decrease in rounds. So we minimize proof size this way, so the verifier likes that. On the other hand, there are more rounds. That's sort of the maximal number of rounds. But, often it doesn't matter because you're going to get rid of the rounds with fiat Shamir. So, and then the prover likes it because the fact that these are multilinear extensions turns out that there are clever things you can do to make the SumCheck prover really fast. And that I don't want to get into in more detail today. But again, that is exploiting multilinear Lagrange interpolation. So it's exploiting that a twiddle of x is the sum over all I in 0, 1 to the log capital N of a I times, the ith Lagrange basis polynomial evaluated at x. It heavily exploits this, the sum check prover being quick, fast to implement, heavily exploits this expression. And yes, there are analogs of this if you deal with non-multilinear things, but kind of the more variables there are, the nicer things get, is kind of the way I would put it. So let me leave it at that. So multilinear is sort of beneficial for both the prover and the verifier. Again, the one downside of using multilinear things, it sort of maximizes the number of rounds, but minimizes like the size of the prover's message in each round. So if for some reason you really don't like that large number of rounds, you might not want to use multilinear things. But if you don't care about those rounds because you're going to get rid of it with Fiat Shamir, I think there's typically the multilinear is a good way to go. Again, there are very subtle issues that come up in different applications that might potentially change that. But I think this is the general message.
Thanks a lot. It's super helpful filling this gap to
Quick
understand
question.
what's going on.
Yeah, thanks for the question.
Someone asked if the function EQ R of X needs to be pre-processed. I'm not super sure what they mean, but the question is, do we have to pre-process EQ of R of X?
Yeah, great. So you're getting at exactly the new ePrint that sort of gets rid of the cost of EQ for the prover, basically. But what's going on? I'll say a little bit about how efficient sum check proving works. I think that's worth spending time on. I'll try to keep it short. So in this particular application, let me copy this down here. Okay, so the way the prover works is like at the start of the protocol. Remember, a, little b, little c, twiddle. Like these are multilinear extensions of vectors, and we described last week or 2 weeks ago what that means. So at the start of the protocol, the prover is really fast. If it literally just stores, I guess most people would probably visualize like the vectors themselves. So the prover and its data structures, like its storage, its memory. So it just stores little a, little b, and little c at the start. In round 0. Okay, and actually, the standard thing to do is for it to also store all evaluations of EQ. So this is what the pre-computation question is asking about. Like, does the prover need to store EQ twiddle of r comma x as x ranges over 0, 1 to the log n? And so like the standard way to implement the sum check prover, we've got 3 different sort of functions or vectors depending on how you view them here, A, B, C, and EQ. And the standard way to implement the sum check prover, the prover at the beginning would be storing all 4 of those vectors, including EQ. Okay, but it turns out that while little a, little b, and little c are totally unstructured, like they in general could be arbitrary vectors, EQ twiddle is like incredibly structured. Okay, so in particular, I can write like EQ twiddle, like I can take x and split it in half. So I can write it as like x1 comma x2, where each of these are in 0, 1 to the n over log n over 2. Yeah, and then I can write EQ twiddle of r comma x as let me split r in half as well, r1 comma r2. So R1 is and R2 are also in now. So I guess these are in field to the log n over 2. So I can write EQ twiddle of r comma x as EQ twiddle of R1 comma x1 times EQ twiddle of R2 comma x2, right? And this is happening because like this equality function operates bitwise, right? So EQ twiddle, we've written it down before. It's like the product over each of the log n variables of r and x of ri times xi plus 1 minus ri times 1 minus xi, right? This is saying like two things are equal if and only if like they're equal coordinate by coordinate. And so that creates this, I call it like tensor structure or multiplicative structure in EQ twiddle. And as a result, it's like it's not really necessary to evaluate this entire vector of size n of EQ twiddle r comma x evaluations, right? Instead, we can evaluate like two vectors of size n to the 1/2. So we can have a vector EQ twiddle of r1 comma x1 as x1 ranges over 0, 1 to the log n over 2. So this is size root n rather than n, and similarly another size root n vector, which stores all EQ twiddle of r2 comma x2, right? And now anytime the sum check prover wants to know EQ of r comma x, it can just look up EQ twiddle of r1 comma x1 and EQ twiddle of r2 comma x2 and multiply the two together. But then if you're even a little more clever, you actually don't even have the prover really pay for this multiplication. So somehow, and this is, you'd have to read the ePrint to see, somehow, the sum check prover doesn't even pay for this multiplication. Okay, but yeah, to summarize, like the cleanest sum check prover implementation in practice applies, to like a g of x, where g is a product of like two multilinears or two or three multilinears. And then, that you have the situation where the prover stores, if these are the multilinear extensions of two vectors at the start in round 0, the prover's storing these two vectors explicitly, but then after round 1, the vectors effectively get, half the size, they wound up halving in size. Again, I'm not getting into the details. In round 2, they have again, and so forth. And, so if you just, put in a third vector, here, and ignore the fact that like EQ twiddle, and ignore the fact that this vector is highly structured, the prover would be, pre-computing three vectors, each of size, number of terms being summed. But because EQ is so structured, the prover, it turns out, this is sort of only being recognized in the last month or something, doesn't need to store all of EQ, but rather can store two square root n size vectors, instead of one size n vector. Right, and it's not just a space savings. It's like, these two square root n size vectors, they only take square root n, pre-computation time instead of n pre-computation time. And so this is a low order. So like order n time, like to compute the whole size n vector is a constant factor of total sum check prover time. So maybe that's like 30% of total prover time was just computing this equality vector. And so now if you, once you recognize that the prover doesn't have to compute that whole equality vector, but rather can just compute two size root n vectors, you actually, speed up the prover by a constant, like a 30% speed up or something. So that is the answer to, does the prover need to pre-compute this equality vector? Turns out it doesn't, but like that's a very recent development. If you're kind of naive about things, then it does. But it can do it in linear time, linear in the number of terms being summed. Okay, more questions? No. So we're happy with the sum check protocol.
Someone just asked to speak, so he's going to hop on, see if he has a question. Rashid?
Yeah, thanks. So going back, I just wanted to, since no one asked a question here, I just wanted to go back to the rounds when you mentioned that, with high degree of probability, when a verifier picks a point and then the prover evaluates that polynomial at that point, and then we do like several rounds to make sure with high degree of probability to tell. So like, just to summarize, what is that? So first of all, like, what's the rounding, those rounds? What are they for? And like, what are they called? And in which like context are we using those?
Yeah, so there's one round per variable of the polynomial being summed. And the point of each round is to sort of cut one variable out of the sum that the prover is making a claim about, right? So at the very start of the protocol, the prover is making a claim. Let me just remind you what the original claim was. So, right, the goal was to compute sum over x in 0, 1 to the n g of x. Yeah, so the original claim involves 2 to the little n terms. Okay. Now at the end of round 1, the provers actually made it so after round 1, the provers kind of left with a claim. The claim is that S1 of R1 equals sum over x2 to xn in 0, 1 to the n minus 1 of g of R1 comma x2 up to xn. So the whole point of the first round was to get one variable out of the sum that the prover is making a claim about. Right. So in general, at the end of round I, the prover's sort of implicit claim that it's left with, so P's claim at the end of round I is that SI of RI equals sum over XI plus 1 up to XN of G of R1 up to RI XI plus, so these are in 0, 1 to the N minus I, XI plus 1 up to XN. So that is the point of each round, is to force the prover to make a claim about the value of a sum, where now there's like one fewer variable being summed over, and hence the number of terms in the sum is half as many as there were in the previous round. And you want to do this reduction, getting rid of one variable at a time from the sum in a way such that like the prover's original claim is true if and only if the claim it's left with is true, up to some small soundness error in each round. Okay, so that's the point. So that after n rounds, we've actually cut all variables out of the sum, and now the prover's been forced to make a claim about a single evaluation of g, the polynomial that originally was being summed over all 2 to the n Boolean inputs. Right. And then again, the hope is, the applications have to worry about this. The hope is that getting this one evaluation of G is much easier for the verifier than computing the original, thing that involved 2 to the n evaluations of G. Okay, so that's the point of each round. Originally there's n variables being summed over, but by the nth round, there's no variables being summed over, and so there's just one evaluation of G that the prover's made a claim about. Right? Again, we make sure that the prover's original claim is true if and only if this final claim is true, unless there's some round that the cheating prover got lucky in, and SI of RI happened to equal HI of RI, where HI is the honest prover's round I message, and SI and HI are not the same polynomial. Okay, did that clear things up? Did that answer the question?
Yeah, actually it did. Yeah, thank you.
Great.
We have another question. Go ahead.
I have a question. So about the sum check over the hypercube for a given polynomial G.
Mm-hmm.
So I don't know if when we do a sum over the hypercube have a size 2 to the n. So I was wondering if we can just put all the G of x in the bottom of the circuit, and we keep just adding by a couple, let's say by pair, until we get the sum over the hypercube, and the check can be just checking a path on this, let's say, circuit. It's not really a circuit, but we just keep adding by pair. So this is my question. I don't know if it is.
In the case you describe, it sounds like you're describing the verifier doing the entire computation, right? Even though you're putting it into a circuit.
No, the verifier will just let's say send an index, let's say index of any, he will choose a pair of two elements. Okay, the prover must do the job before, because he must compute all the sum until he will get the sum over the hypercube. And I don't know, the verifier can just ask, like let's say a Merkle tree, but it's not really, there's no hash in here. It's just adding by two elements. I don't know if my question is okay or.
So I think your question is foreshadowing some major applications of the SumCheck protocol, but is a little hard to answer till we just see those applications. So I will say, like, let me see what I can say now. I do want to, so okay, so two major applications of the SumCheck protocol. Applications is in quotes here because one of these is totally impractical. So one is an interactive proof for what's called SharpSat. So this means counting the number of satisfying assignments of what's called a Boolean formula. And I think I did sketch this a few weeks ago, but it might be worth me describing it again now that we've seen how the SumCheck protocol works. So this dates back to like 1990. Like this was literally from the paper that introduced the SumCheck protocol. So this was the first application of SumCheck. Now the reason this is impractical is for n-variate Boolean formulas. You know, the prover in this application of the SumCheck protocol, or what? How do I want to say this? The sum just involved, even in defining the problem SharpSat, the sum involved, like there's no way, even if there was no proof needed, like just solving the problem involves 2 to the n terms. Okay, and we, you know, in SNARK applications, the number of, you know, like they're, you know, if you're computing x and 0, 1 to the n g of x, in SNARK applications today, this n is like log circuit size. And so, you know, summing over 2 to the n terms is like circuit size. Okay, and so that's fine. Like we're fine with our prover running in circuit size time. Like it, you know, it has to run at that time just to evaluate the circuit. But you know, here n is not the size of the, is not log size of the circuit. It's like the number of variables in the circuit. So that means it might be close to the size of the circuit. So 2 to the n is like the 2 to the circuit size. Now, this is unavoidable because, like, you know, even if you ignore the requirement for a proof, even if you just want to solve SharpSat, we suspect that that requires 2 to the circuit size time. So there's no avoiding it. It's just the problem is like way too hard a problem than anyone solves in the real world. And that interactive proof worked very similarly to, I think, what you were sketching, which is the G, you know, so this you know, summing over x and 0, 1 to the n of g of x. In this application, these x's are assignments to, you know, they're Boolean assignments to the n Boolean variables of the formula. Of the, you know, of the satisfiability. And this G is some kind of low degree extension polynomial of like the function computed by the formula, right? So that G of, you know, if x is Boolean, G of x equals 0 if x satisfies the formula and 1 otherwise. So sorry if X does not, and it's one if G of X is one if X does satisfy. So that summing over all assignments of G of X is just summing over, it's just counting the satisfying. So that was like literally the first application of the protocol, and in a sense, the prover is close to optimal because you can actually implement the prover in pretty close to 2 to the n time. Problem is that 2 to the n time is still impractical. It's like it just takes 2 to the n time to solve. That still means it's too hard a problem. And so the second application is from 2008, the GKR protocol. Okay, and now here it's something similar where there's like a circuit or a formula, but there's like a fixed assignment, and so there's some fixed X, and I don't know, and let me call this a circuit C, and the prover claims C of X is something, right? And what the IP equals P space approach would be to kind of turn the entire circuit all at once into one big polynomial G. Okay, but like the GKR approach says, well, that's no good. That's no good because then your sum is just over too many terms. It's over circuit size many terms, which is too big for the anyway, I'm waving my hands here. And so what the GKR protocol will do is it will actually apply the sum check protocol many times. We'll talk about this in great detail in a few weeks. So it won't apply sum check just once. It will apply sum check once per layer of the circuit, starting with the output and moving towards the input. And so, in the last application of sum check, the prover finally sort of deals with the input, the multilinear extension of the input alone, right? And so in particular makes a claim about the multilinear extension of the input at a random point, right? And by multilinear Lagrange interpolation, implemented, intelligently, the verifier can compute X twiddle of R in time linear in the size of X. Okay, and so yeah, that's we'll see applications more and more. Again, it's like sum check protocol is a hammer that is very natural and powerful, but you just have to see the hammer used like 3 to 6 times before you can possibly get comfortable with it. And so if you sort of apply that hammer only once in the contents of circuit sat, you will potentially wind up with like too many terms in the sum, and so the prover is very slow or something like that. But if you apply the hammer, over and over again, you might never have all that many terms in any individual, sum. And then finally, the prover is left making a claim about the input alone. And, there was a question earlier today, like where does multilinear Lagrange interpolation and multilinear polynomials come in? And the answer is always, well, the polynomials we apply sum check to are built out of multilinear ones. And here is a particularly nice multilinear one that the verifier on its own can evaluate over time. But importantly, this is a polynomial, a multilinear extension of something known to the verifier. And so like the verifier has to read this thing anyway. And so linear time in the size of that thing is totally fine for them. Okay. So maybe not my cleanest answer, but yeah, I think your question was hinting at how SumCheck is actually used, but the details are, we'll have to spend future weeks on them.
Okay, thank you very much for the explanation.
Sounds good.
Don't see any more questions.
Okay, sounds good. Let me think for a second then about so we're over an hour in. So let me limit myself to, I think we'll see more applications next week. So I'll limit myself to just a little bit more discussion of implementing the prover. Right. So I was very, very sketchy before. Sorry, there's let me just give me 1 second. So I was very sketchy before about how you actually implement the SumCheck prover. Like the SumCheck verifier is very simple, and you know, every round it just checks that SI minus 1 of RI minus 1 equals SI of 0 plus SI of 1. And, you know, these are each like degree 3 univariate polynomials. So it's just like a very simple check. And this is the verifier. And so it's pretty much trivial to implement the verifier. But the prover is a little more interesting. And so, you know, when there was the question about, you know, does the Spartan prover have to like compute this like equality function, I gave a little sketch of kind of what you know what happens for in the prover's, you know, memory or, you know, its data structures. But let me just elaborate on that a little more, and then we'll call it a day. So if you look at the prover, like the honest prover's message in round I, it is the honest one I called HI of X, and that was the sum over xi plus 1 up to xn in 0, 1 to the n minus I of g of r1 up to ri minus 1 x xi plus 1 up to xn. Okay. And for the moment, let's, you know, like in Spartan, remember, just to have a concrete application, you know, G was EQ twiddle of R prime comma X. I'm sticking a prime here just to not over, you know, since I used R for the SumCheck variables. Yeah, EQ of R prime comma X times A twiddle of X times B twiddle of X minus C twiddle of X. So just to, yeah, so for the moment, let's just treat G as like a black box, like it's just some low, you know, low degree polynomial. And then I'll say more for this particular G used in Spartan. And so what is the natural way for the prover to compute HI of X? That, you know, again, this is a degree, say 3 polynomial in one variable. Okay. And so the natural way to do it is to compute, is to evaluate HI at 4 points, right? Because HI is defined in terms of a sum of evaluations at G, it's very natural to, for the prover to compute HI in evaluation form, right? Via 4 evaluations instead of the standard monomial coefficients, right? So you can specify a degree 3 univariate polynomial by specifying any 4 of its evaluations. So let's say the prover will compute HI of 0, HI of 1, HI of 2, and HI of 3, say. Okay, and so that means the prover needs to compute, so what's HI of 0? It's sum over xi plus 1 up to xn and 0, 1 to the n minus I of g of r1 comma ri minus 1 comma 0 comma xi plus 1 up to xn. You know, in general, let me, yeah, you know, HI of 1, you just replace the 0 with a 1, and so forth. You know, HI of 2, you replace the 0 with a 2, and so forth. Okay, so This mean what the sum check prover does is, so in round I, the sum check prover really needs to know evaluations, like all evaluations of G at points of the form R1 up to Ri minus 1, comma, 0, 1, 2, 3, comma, B, where B ranges over 0, 1 to the n minus I. Okay. And I don't want to say this. So if we just treat G as a black box, like in round I, this means how many evaluations here are there? So it's something like 2 to the n over 2 to the I, maybe times 4 or something. Evaluations of G. Okay, so in a world where if G could be evaluated at any point in constant time, this would actually be really, we sort of, our life would be great, like it's obvious how to implement the prover, the sum check prover in total time. Basically, sum. So we got sum over all rounds I. So I equals 1 to log to n of 4 times 2 to the n over 2 to the I. Okay, and this term, which again, so this is like 2 to the 4 times 2 to the n minus 1 plus 2 to the n minus 2 plus 2 to the n minus 3, so forth. This turns out to be dominated by the first term. So this is something like 8 times 2 to the n. Okay, remember 2 to the n is the number of terms in the sum, in the original sum. Right. Okay, so what this is saying is, like, if you could evaluate G, the polynomial whose evaluations are being summed at any point really, really quickly, a linear time sum check prover is kind of trivial. Okay, so again, so if G is really evaluable at any input, like super duper fast, then linear time sum check proving is trivial. Okay. So the complication is when you actually come into applications, G looks like this sort of stuff. And now it's not obvious that you can evaluate G at any point in like linear time. In like constant time. Okay. And so that's what, like, there's been, over a decade of papers like trying to address. And we've gotten really good at it, and we have addressed it now. So like in Spartan, we have the sum check prover time actually down to like a leading constant of 5. So even better than that 8 I had below. So like 5 times the number of terms in the sum. Okay, and I'm just going to sketch a little bit about. I sort of said a little bit before. Let's pretend like G of X was just a twiddle of X times B twiddle, where A is a length to the n vector, and so same with B. Okay, so what's going on is like if I want to evaluate a twiddle at a point, like that will take order 2 to the n time if A is like an arbitrary vector using multilinear Lagrange interpolation. So that seems really bad. That's bad. because I said we could get a linear time assumption prover if a total of R could be obtained in constant time. Like we want, we get a linear time prover, very easily if this were order one time. It's very, very much not order one time. It's order 2 to the n time. Huge difference. This is the difference between the prover taking, difference between what we want, which is order 2 to the n time for the prover, and the square of that. So why is everything okay? Everything is okay in the end because in round one, the points that the prover must evaluate G at, well, they're not totally unrelated, right? They are of the form, so no variables have been bound yet. So it's just like 0, 1, 2, 3, comma B, where B is in 0, 1 to the n minus 1. These are the points. If what's going on is if the prover, already has A and B in its memory, then, evaluating, let's first start with looking at just 0, 1, forget about 2 and 3 for a second, right? So at any point of this form of, X in, that's Boolean. So X in 0, 1, comma B, here all entries of B are in 0, 1, and this is in 0, 1, so X is just Boolean. So, G of X for such an X is just A of X times B of X. That's what it means for G to be A total of X times B total of X, right? Like because A total and B total extend A and B, right? If you feed in a Boolean thing to A total and B total, you're just looking at entries of A and B themselves, right? And so for the entries that are in round one, at least if you don't worry about 2 and 3 right now, right? It actually is constant time prover to evaluate G of X at those points. Because the prover has A and B in its memory, each evaluation is just like one read into A, one read into B, multiply them. Right. And then it turns out that this is sort of like a twiddle of 2 comma B is a simple expression of Boolean evaluation. So it's 2 times a total of 1 comma B plus 1 minus 2 times a total of 0 comma B. And similarly, a total of 3 comma B is 3 times a total of 1 comma B plus 1 minus 3 times a total of 0 comma B. And this is just this follows directly from you can just check this. In general, a total of C comma B is C times a total 1 comma B plus 1 minus C times a total of 0 comma B. And this is, you can see this because the left-hand side is multilinear in C and B. And you can easily check that it agrees with a twiddle when C comma B is in the hypercube. Right. Yeah. So let me call this an exercise. And so the dealing with the evaluations 2 and 3 in each round are not different from dealing with the Boolean evaluations. I can get the evaluation for for that first variable being 2 by looking at the 2 Boolean evaluations and doing just a little bit of extra work. Similarly for 3. And so what's going on is like these, while a twiddle evaluated at like an arbitrary points takes, order 2 to the n time to get that evaluation. In round 1, the prover only needs to evaluate a twiddle and b twiddle at points where actually it can get the evaluations in constant time. Okay, and then you know, if you're a little bit clever about things, you can maintain that property round over round, and that's what I was hinting at before with the notion that the prover's data structure has in size of each round. So using this expression right here, let me actually bring that up, and I'm just about done for the day. Where do I want to do this? This isn't working. Okay, that's not working. Undo. All right. Right. So let me just in round I, the prover needs g of x for all x of the form. So you know the first I minus one variables have been bound. The ith variable has to range over like 0, 1, 2, 3, and then the remaining variables are Boolean. Okay, and so just focus on round 2 for a second. And so like at the start of round 2, you know what the prover needs. You know, we're like if G is a twiddle times b twiddle, right? It needs a twiddle of x and b twiddle of x for all x of this form. Yeah, and actually at the start of round 2, only one variable has been bound. Sorry. Yeah. And so, you know, I'll just show you how this is done. Like, how does it make sure it can get all these evaluations in constant time per evaluation? What's going on is, you know, at the start of round 0, we have A and B stored explicitly. At the start of round 1, what the prover will store explicitly is a vector of half the length, which will be all evaluations of a twiddle of R1 comma B, as B ranges over 0, 1 to the n minus 1. So we and B twiddle, it'll store B twiddle of R1 comma B as well. That's a vector of half the length. And you know, this expression here tells you that a twiddle of R1 comma B is just R1 times a twiddle of 0 comma B, or 1 comma B, plus 1 minus R1 times a twiddle of 0 comma B. And so that means that each entry of this vector, which is of half the size of the original vector, can be obtained, you know, by looking at, you know, so the bth entry of this vector can be obtained by looking at a twiddle 1 comma B and a twiddle of, you know, or I guess that's 0B and a twiddle of 1B. So you can, you know, compute each entry of this vector in constant time given the preceding round's vector. And then given once you compute these half-size vectors, the prover can get every evaluation of G needed in round 1 in constant time per evaluation. Right? And then in round 2, you can do the same thing, where now you know, you'll be storing a twiddle of R1 comma R2 comma B, where now B is only ranging over 0, 1 to the n minus 2 rather than just 1, and same for B twiddle. And in that way, sorry, I overloaded B. Hopefully you got the idea. In that way, the prover at all times, given its data structure, is able to compute every single evaluation that it needs in the subject protocol in constant time per evaluation. And you know, the update to the data structure in each round, you know, gets computed in time, like you know, linear in the size of the data structure at that round, but in each round, the size of the round, right? You know, the data structure only has size 2 to the n minus I. You know, so the total prover time across all rounds is proportional to, you know, again, sum over all rounds I of, you know, 2 to the n minus I which is proportional to, 2 to the n. Basically the first round dominates, something like that. Okay, so that's what's going on. So just as a final one sentence summary, in round I, the prover has to evaluate the polynomial being summed at 2 to the n minus I terms. Okay, those points, those terms that it has to evaluate g at, they're not unrelated. They're very closely related. They all have the form R1 up to Ri minus 1, 0, 1, 2, 3 for the ith variable, and then Boolean for the remaining variables. And so it's possible for the prover to maintain a data structure round over round that lets the prover obtain each of the necessary evaluations in constant time. And so as a result, over all, n rounds of the protocol, it's actually the first round that dominates. And that first round is very obviously like linear time, linear in the number of terms being summed, because that first round, as I said before, each term involves, just an entry of the original vector A multiplied by the corresponding entry of the original vector B. So that's obviously constant time per term. Okay, so that's the SumCheck protocol. That's also, the Spartan application from last week. And so next week, I want to cover just some more applications for practice. I'll probably talk about matrix multiplication. And triangle counting. It's possible that's all I discuss next week. And then the following week, I think we'll hit the GKR protocol. Yeah, so that'll be the next 2 weeks. And hopefully by the end of those 2 weeks, we'll be comfortable with how the SumCheck protocol gets used, and proceed from there. But let me know if you have any questions after this, rambling exposition of the SumCheck prover.
There are a couple questions. One second.
Okay.
Can you hear me now? Yes,
Yep.
it should work. I have a very quick one. Is this approach that you showed last, which is the quicker one, does it works because of binary decomposition? Is it the cornerstone? Is it the cornerstone of it?
Say that one more time. Does it work because of binary
Decomposition of this high? If I understand correctly, the hypercube is more or less just binary decomposition, isn't it?
Yeah. I mean, what I would say is the key property is this equality. Where did I write it? Sorry, give me 1 second. It was the thing that I tried to move around and then gave up. It's this equality here. So the key, everything works so great because every time. So what this is saying is, if I fix it, so if A total is multilinear, if I fix a variable's value to any field element C, not just binary, not just 0, 1, but any field element, C, the resulting evaluations, if everything else is binary, but whatever. Well, so no, let me forget about the resulting evaluations. Are regardless of the remaining variables, are a super simple, constant time computable expression of like C being 0, 1 only. Yeah, and this is coming. This is a really nice property of multilinear things. Okay. And that's what the prover's exploiting, and that's what I was trying to give a sense of before when I said, multilinear things are really nice, like not just because they minimize proof length of the sum check protocol, but also because they ensure the prover's really fast. And yeah, so
Just the source of the question was, if I'm getting right, the difference in structure between the first application that was impractical and the second one, which is practical. I thought it's the quantity of structure in it, and it's not that easy to pick up.
yeah. The impracticality of the SharpSat protocol is not necessarily because it's not using multilinear things. It's really coming because they're taking an entire like computation, like a Boolean formula or something.
It's
And
the number of hits of the hammer,
yeah, it's sort of
like it was
um,
before.
it's really just because they're applying sum check to something with too many variables. in that application, the number of variables is of the polynomial that sum check is being applied to is equal to like the number of inputs to the circuit. As a result, you're basically summing over all possible assignments that the circuit might be evaluated on. So it's not really like a multilinear versus non-multilinear thing. It's just like there's just too many variables in the polynomial they're dealing with. And the reason there's so many variables is roughly because rather than the prover committing to one assignment and then the proof just being about the evaluation of the circuit on that one assignment, instead the prover is proving something about the circuit's behavior on all possible. The multilinear versus non-multilinear thing is really it's not the difference between an exponential time prover and a polynomial time prover. It's that difference is coming in because like in SNARKs, the prover commits to one assignment to the circuit and only proves, how the circuit behaves on that assignment. Or again, in the IP equals p-space result, the prover was proving something about how the circuit behaves on all possible assignments. The multilinear stuff is more, about the difference between. It depends how naive you are, and it's sort of, if you're very naive, it might be the difference between like a quadratic time prover and a linear time prover. If you're less naive, about how you do non-multilinear stuff, maybe it's the difference between like an n log n or n log squared n time prover and an order n time prover. And those log n or log squared n factors are really, really important in practice. But the complexity theorists wouldn't have really cared. So the complexity theorists do care about the difference between like the first application of sum check and how it's used today. But that's really again due to today the prover commits to one assignment to the circuit and just proves what the circuit does on that one assignment rather than proving a statement about all possible assignments.
Thank you. Yeah, it's clear. Thanks.
Yeah, a little better. Yeah, this multilinear stuff is just super nice. That if you were using some kind of degree 2 extension of A and like there was no structure to that degree 2 extension or something, just like this would not hold at all, right? Like it really might be the case that in the worst case, like the only way to evaluate like a hat of C comma B if this were like degree 2, not multilinear, degree 2 in each variable or something, would be like some kind of as a sum over all B in 0, 1 to the n minus 1. But when you deal with multilinear things, they really have this nice kind of they kind of intuitively operate like one variable at a time. And so you get expressions like this. And so rather than it taking, like linear time per evaluation to get these, the evaluations the subject prover cares about, you wind up with it taking constant time per evaluation. And that's why the subject prover in the end, in most applications, takes linear time rather than quadratic time or something like that.
Thank you.
Other questions?
Yeah, I just wanted to ask real quick. So, considering that, so the subject protocol is interactive, and what are the like modern, like I guess, advantages or like modern applications of this protocol? And yeah, and then like if it doesn't, if it even makes sense, or if it's possible to like apply like Fiat Shamir or something to make interactive, or
Yeah.
thank you.
So people, great question. So people basically just they always use Fiat Shamir, essentially. So it is a public point protocol, right? The messages from verifier to prover in the subject protocol are just random field elements. So you can make it totally non-interactive just with Fiat Shamir, and that's what people do. That's how people tend to use it. And my perspective on like how it's getting used in like Snark design today is roughly that the subject protocol, if you run it interactively, there's no cryptography. Yeah, it's information theoretically secure. The prover is just doing like field additions and multiplications, only a linear number than linear in the like number of terms being summed or whatever, which in Snark applications is like the number of gates that you're proving a statement about or whatever. And so those field operations are very lightweight. They're much cheaper than if you were, like N field ops are much cheaper than like N hash evaluations, much cheaper than N group operations, much cheaper than N like, group scalar multiplications or whatever, which some snarks actually do need. Yeah, so you sort of, the subject prover does a bunch of field ops kind of in exchange for doing those field ops, which are not that pricey. The snarks that do use the subject prover wind up having the prover commit to a lot, right, cryptographically commit to a lot less data. Okay. And in addition, there are other like downstream benefits, like not only is the prover committing to less data, but if you don't use the subject protocol, like just computing the extra data to be committed is itself expensive. Forget committing to it, just figuring out what the data is. So there's often like some kind of quotient polynomial, and even if the prover doesn't explicitly commit to it, the prover does have to somehow compute that quotient, and it's just expensive, and those values might be big, even if the you're dealing with the computation, like big meaning like arbitrary field elements, where even if you're dealing with the computation where all of the values arising in the whole computation are at most 32 bits or something. And so, people are starting to appreciate that like, this subject protocol kind of, you pay a little bit of field work, which is generally cheap. And in return, you do less field work elsewhere in the protocol and commit to less data and stuff like that. And so the prover is overall faster. Was that a little bit helpful?
No, yeah, absolutely. Thank you.
So Fiat Shamir is cryptography, but like that is not, that cryptography, that hashing is just getting applied to the proof. Right? And the subject proof is pretty small, right? It's like log number of terms being proved, which is like, so it's like you're hashing a like log circuit. And so like, Fiat Shamir is not a prover bottleneck. Now you can get into situations where its costs are meaningful if you bring in Snark recursion, because then the prover has to prove it did Fiat Shamir correctly and stuff. If you're, if you ignore stuff like recursion, Fiat Shamir is like, very, very lightweight cryptography as far as the prover is concerned. this whole, like, there's no cryptography in the SumCheck protocol, I basically say more of this whole do use fiat Shamir. Yeah. Okay. Any more questions?
That is it.
All right, great. So again, the plan is to see a couple more applications of SumCheck because I think, you know, you have to see several to get comfortable with how it's used. And then, so we'll do that the next couple weeks. And after that, we'll probably turn to polynomial IOPs based on univariate polynomials. So, you know, basically the alternative to SumCheck out there. Actually, those don't take the cover, and after that, we polynomial commitment teams, and that's actually what we'll spend probably the bulk of our time on. So anyway, that's just a little bit to look forward to over the next coming weeks, and thanks for staying to the end as always. See you next week.